Is it recording? Oh, yes it is. All right. So, this will be lecture 2 in Sustainable Energy and Society. And today we're going to talk about climate change. And we're going to talk a little bit about coal. This coal stuff is not in the book, so it's just culture, I guess. So, let us proceed. First of all, we talked about this a little bit. Do you believe mankind is warming the globe? So I think we had one person who said that the climate might be changing, but they weren't convinced that we could prove that mankind was behind it, right? Is that what you said? Did I capture your thoughts? And other people pretty much thought that, yeah, we were changing the globe, the climate. Is that correct? Does anyone think we're not? Okay, great. So I have to press these magic buttons here. Preset 7 will now show the screen. Okay. So this is what we were talking about last time. I'm going to claim it's likely that using fossil fuels changes the climate. I'm going to present some evidence and you can see if you agree. We definitely need energy because we have to cook our Pop-Tarts. So to do that, we burn fossil fuels. When we burn fossil fuels, that produces carbon dioxide. Carbon dioxide increases the temperature of the globe via the greenhouse effect. Is this the only thing that's increasing the temperature? Who knows? Does that change the climate? Maybe. Since we need energy, it would be nice if we could find new sources of energy that don't produce CO2, and then maybe we could slow down climate change and not burn Earth to a crisp. So, how bad is the situation? This was in the book. The world greenhouse gas emissions for the entire world is 34 gigatons of carbon dioxide emissions, that's what the E stands for, per year. And this, that's the area of this block. This is tons of carbon dioxide emissions per year per person, and this is people. Population in billions, we have about 6 billion people. So if every person on the planet is effectively producing more than 5 tons of bad emissions per year, this is a 2000 number. And the emissions increase the average temperature of the Earth. Notice that although people are created equal, we are not polluting equally. So this is for the whole world on average. The United States is above average. We do more than our fair share to creating greenhouse gases. This plot has North America is here. So this is people on this axis and gigatons of emissions on this axis. So the total carbon dioxide emissions by a region of the Earth is given by the area of this rectangle. And our rectangle, we don't have that many people, but per person, we create a lot. The area of this rectangle, you might say, is comparable to the area of this rectangle, which is Asia. So there's a lot of people. They're not producing as much carbon dioxide per person as we are. But since there's so many more of them, perhaps their contributions are equal. Oceania, they're pathetic. They're right there. They're very skinny, hardly any people. Here's Europe, and they have more people, fewer carbon dioxide emissions per person. Notice that we are far and away emitting more. North America includes Canada and Mexico, so it's not all my fault. This is the Middle East and North Africa. Here is South America. Here is Central America and the Caribbean. Not that many people there. They also don't produce that much CO2 per person. Asia we talked about. And this is Sub-Saharan Africa. So we emit the most per person on average. What trend do you notice, or what do you think contributes to the fact that these areas produce less emissions per person and these areas produce more? What kind of social factors? Yes?
A lot of those regions that produce less per person are underdeveloped. You have more third world countries or parts of Asia that aren't really, you know, they're not modern in the sense of the United States.
Yeah. So they have less technology infrastructure. They have a lot of people living in rural areas who don't even have electricity, for example. So they don't have as much opportunity to create carbon dioxide as we do. We do. And I see that the I cannot be seen in this camera, so I'm just going to try adjusting the lights and see if that changes anything. Survey says no. Does any of this improve anything? You guys can still see all right, right? I think this will be a little bit better. Okay. So our emissions for North America is 24 gigatons of carbon dioxide. Carbon dioxide is a gas, so try to imagine how much is a gigaton of gas. Wow. Each year per person. Oh, sorry, 24 tons. Still a huge amount. Multiply by 0.25 gigapersons. That's how many we have in our area, and that will give us the area of this rectangle. So as a continent, we emit 6 gigatons per year per person from this data. So we have to manage units. So when we multiply these things together, oh, I don't have a pointer. I wonder if this mouse will point. Cool. So we have 24 tons of carbon dioxide emissions per year per person. So we have 1 over people. I took the per person out here. And then times 0.25 gigapeople. So the people will cancel. For those of you who don't do a lot of units contributing. So you know that anything over the same thing equals 1. So we can cancel those out because multiplying by 1 doesn't mean anything. I still have giga left. And I'm going to have 24, I took the numbers over here, times 0.25. Tons of carbon dioxide emission per year comes from here. There's no people anymore. There's the giga. So that gives me 6 gigatons of carbon dioxide emissions per year. We're going to be doing a lot of this. We're going to be converting from kilowatt hours to joules and seconds and things like that. Yes?
The lowercase e, is that just for emissions?
Yeah, that just means emissions. Yes.
I thought the E was saying that it's CO2 equivalents. Like, this isn't only CO2 that people are emitting, but this is like taking all the greenhouse gases and putting it in terms of kind of an equivalence, like a standard unit, like in warming effects, it's this much CO2.
Maybe it is. I don't remember, actually.
Yeah, in the book it said E means equivalent emissions, so
Okay.
it includes methane, nitrous oxide, and carbon dioxide.
Oh,
equivalent.
gotcha.
So it's methane and nitrous oxide and carbon dioxide.
Okay, so, okay, thank you. I appreciate you clearing that up. So it's not exactly emissions, it's equivalent. Okay, so now, when did climate change start? Well, that's an interesting question. Somebody drilled a bunch of cores from some ice at Vostok Station in East Antarctica, and they measured the carbon dioxide here as a function of how long ago. And you see that there are these natural cycles that have been going on since time began. Time began here. So the temperature went down and the carbon dioxide went down. So this purple line is temperature and the black line is carbon dioxide. And they seem to be more or less in sync. The temperature goes up, carbon dioxide goes up. Or maybe carbon dioxide goes up and the temperature goes up. Carbon dioxide comes down, temperature goes down. We have these various long period cycles with some other shorter cycles in there. But this data only goes up to about 2,000 years ago. Okay, so that's the best that they can determine the depth of the ice and the age of the ice. So the question is, what happened since then? Before we go on, let's look at these numbers. This is minus 10 C, 5 degrees C. This is freezing. Antarctica doesn't get above freezing that much. 5 degrees C. And over here we have between 7.5 and 8.5 parts of, say 8.5, sorry, concentration. Maybe it'll be more useful to look at 181 to 315, I forget what this unit is, ppmv, parts per million something. Now, if we look in the last 1,000 years, we see that we're around 260 ppm. Let's see if that's about where we left off. This was 181, this is 315, so we were right in this region. And now we're totally expanding that scale because that was hundreds of thousands of years. So now we don't see, we're in a very small part of that other graph, so we're not seeing a lot of variation. And this is 1,000 years ago. No, this is year 1,000, sorry. 1,200, 1,400, 1,600. And then all of a sudden, right in this region, the carbon dioxide concentration shoots up. What do you think happened right around 1769? Yes.
The Industrial Revolution.
Invention of the steam engine. Then we started burning stuff to make steam, to do work, to make our lives better. And when we started doing that, you'll see that there's an increase in the carbon dioxide concentration. That previous graph went up to about 315, was it? Let me go back and see what that other graph said. Yeah, about 315. So 315 is about here, so we've already exceeded that, and we're going up more and more rapidly all the time. This is measured in ice cores in Hawaii, by the way. Invention of the steam engine. Cause or coincidence? So is it our fault? The climate has always been changing. We just established that. There's reason to believe that humans are now contributing in a bad way. I'm very suspicious about the steam engine. If you consider coal production in the UK and the world from 1600 to 1900, oh, that's what this graph is. Coal production. So coal production, wait a minute, we need to back up. People were burning coal to get their energy back in the day. And the reason that they invented the steam engine was because the coal mines would flood. They would fill up with water, and it's very expensive when you lose all your people who are digging the coal to replace them. So they needed a way to pump the water out of the mines. And when they produced a steam engine, so this is the first steam engine, and then James Watt made some improvements. We'll talk about the steam engine in a little bit. When they made it possible to pump the water out of the mines so the mines were safer, they could produce more coal. So once they were able to do this, coal production went up. World coal also went up. So if you look at the coal production UK from 1600 to about 1900, 1600 to 1900, 1600, 1900, you can see that it goes up. Units here are billions of carbon dioxide emissions, and the sharp knee in the plot is, as you said, the Industrial Revolution. So, in what time, this is a poll, in what time interval did the coal production in the UK approximately double? So we got a couple of choices, 1850 and 1900, 1700 and 1800, 1850 and 1870. Anyone vote for A? Anyone vote for B? Anyone vote for C? We have some votes for B, we have some votes for C. Pretty hard to read on this graph because this stuff down here is really compressed. It's not changing very much. You know, I can't read this number off this graph very well compared to that number. So let's see if I have the answer. No. Ha! Guess we're going to find out as we go along. So the steam engine was invented, it was first discussed by the mathematician and engineer Hero. This was in Alexandria, Rome. I don't have the date. First successful steam engine was made by this guy, Newcomen. And why do we have a picture of James Watt? I have no idea. Newcomen's engine looked like this, Watt's engine looked like that. This was in 1712, again, pumping water out of coal mines. It replaced 500 horses that were used to power the pumps before that. So before that, they actually hooked up horses to things to make them pump the water out. The improved efficiency engine, which was Watt's, proliferated after 1769. And also, they were able to make the engine small enough to power a vehicle. So here, this is a huge building, essentially. You couldn't hook this up to your car. They didn't have cars. They were able to make a version of that you could. Watt was granted a patent in 1755. He measured his engine in horsepower equivalents. That was actually the first unit of power. So here's Newcomen's engine. There's a cylinder here with a piston in it, and it was open to the air. When the piston goes up, steam would then be drawn in from a pipe that we don't see into this chamber, I guess. Then the water would condense the steam and create a vacuum. So they would pump cold water in here. The cold water would condense the steam. When the steam goes from steam, there's pressure, to water again. It reduces the pressure. That created a vacuum that pulled the piston down. So the piston pulls down, the lever goes up, and there's buckets or something that's pulling up the water. So a chain was attached to a lift pump. That replaced 500 horses. So what do you think the horsepower of this engine was?
500.
500 horsepower! Can you imagine 500 horses? They couldn't have done them all at once. Oh, we have a link. Very exciting, very exciting. Nothing like videos and advertisements. So here's new Cummins engine. So the piston is up. When the piston is up, the steam comes in here, water comes in here. So there's steam comes in from here, water comes in from here, and this is the fire. This is a chamber full of water. It's creating steam. So when this valve opens, steam can go in here and push the piston up. Then they close this, and water goes in and condenses the steam, creates a vacuum, sucks that down. How cool is that? This is how stuff works. One of my favorite sites. Oh, look, we're back. Now, what? There were some disadvantages with that. Did I have those disadvantages on there? Thought I put them in there. Oh, they're lost. So the disadvantage of this technology is that you're heating up, you got steam down here, you're heating up this chamber with steam, and then you put in water and you cool it down again. So the outer walls of this thing were constantly heating and contracting. You spent a lot of energy that you were generating just reheating this cylinder. So it wasn't very efficient. So Watt said, okay, I'm going to separate those two things. I'm going to have the vacuum pump and condenser down here, and here's my chamber with the piston in it, so that the heat was generated and the vacuum was generated down here, and this thing didn't have to change energy. So separate condensation chamber, that's here. Cold water is injected into this smaller chamber. The steam stays here, so the chamber stays hot. Here's a hot well. I think there's a hot water tank here. And when the steam pushes the piston, oh, I probably have a cartoon. And when the piston hits the top, I just finished this. The piston hits the top here. There's a steam inlet valve closes, and a valve to the condenser opens, and there's a partial vacuum there. So then the piston goes back, gets sucked back down. So it actually wastes less heat because you're not constantly reheating that chamber. I believe I have a video of this. Oh, look how stuff works. Hello, where is it? So here, you've got the flames and the steam. The steam goes in here, but the condensation happens down here, and this is a partial vacuum down there, so that this chamber stays hotter. All right, let's take a poll. Why was Watt's modification of the steam engine important? How many people think, well, let's read the choices. Watt said it was more powerful, it was more efficient, or it was cheaper. How many people think it's because it was more powerful? Nobody. How many people think it's more efficient? Everybody. How many people think it's cheaper? We have no idea. Doesn't look any cheaper. Okay, another consequence of coal production. This is a plot of population growth. This is in Britain, England, and Wales. And we have the same number of people, same number of people, same number of people, because you can only burn so much coal, because you can only get so much coal, so you only have so much energy to support so many people. When you started being able to get more energy, then you could have more people, because it was easier to support them. And some of those engines were used to irrigate fields and things like that, so it wasn't just producing coal. So as we had the ability to create more coal, dig up more coal more efficiently, we could support more people. So the world's population would go up, and England's population would go up. Here's England and Wales, here's the world. And if you have more people, they want more energy, so you got to dig more coal. If you dig more coal, you can support more people who want more energy, so you dig more coal. You get the idea. So we have a runaway effect here. So this is England and Wales, they're down here, and here's the world. And again, the scale here is from 0 to 35. On this scale, you can barely see it. But the world population, you can see, is really shooting up. We have a problem with how we're plotting this stuff. Things change quickly. 50 years later, the world is catching up. British coal population peaked in 1910, right there. World coal production still doubled every 20 years. See how it's going up like crazy? It's very difficult to plot. So we either need a very tall plot so we can find out what's going down here, or we need another way. So a thing that engineers do is we use something called a log plot. Log stands for logarithm. So we need a new scale. Basically, we want to stretch out what's going on down here so we can see it better, but we want to stretch this stuff out without stretching this stuff out, like that last graph I had that was as tall as the screen. So what's this say? This says if I want to see the details down here, I can take this part and extend it, but then if I plotted this stuff on the same scale, it would go up to the 8th floor. So we want to change the scale by a factor of 10 or more. Before we go on, I guess we have another poll here. How many times did the world coal production increase between 1900 and 2000? 1900 and 2000. World coal is the red line. We could say 4 times, we could say 20 times, or we could say 110 times. How many people think it's 4? From coal, from 1900 to 200. How many people think it's about 20? How many people think it's about 110? Let's see. World coal production in 1900 is about 2 or 3, and in 2000 it's 20 something. So I'm thinking a factor of 10, 20, somewhere in that range. So we're going to use a logarithmic plot. So what you do here is you're still using the same numbers, but you're compressing the scale logarithmically here. This is 0.1. This is 2, 3, 4, 5, 6, 7, 8, 9, 0.1. So this is actually 0.02, 0.03, 0.04, 0.05, 0.01, 0.1. Now you see this goes from 0.1 to 1. So this starts at 0.1, 0.2, 0.3, 0.4, 0.5, blah, blah, blah. Here's 1. 1, 2, 3, 4, 10. 10, 20, 30, 40. So that's how we compress the scale. When we plot that previous data on a logarithmic plot, it squishes the vertical axis up the top and stretches it at the bottom so that we can get a clearer picture. On a log scale, something that grows at a constant percentage every year, we say grows exponentially, it should look like shoo, like those previous plots we had. On a logarithmic plot, that'll look like a straight line. That's called exponential growth. My slide is messed up. This says log graphs allow us to compare growth rates by comparing the slopes. So this on a log plot still has a steeper slope, so world coal is increasing faster than UK coal in this time period. How do we mathematically describe exponential growth? Let's do an example. Let's say at some particular date that we pick to start, T0, the production of coals is some rate P0. It increases 10 times every 20 years. So we start off with this. After 20 years, we have 10 times that number. After 40 years, we have 10 times the previous number from 10 years ago, or 20 years ago. So that's this, but this 10p, so this 10p0 goes in here, that's 100p0, so we get 100 squared. 20 years later, we have the original amount plus 3 times 20, and that gives me 10 to the third and so forth. So if we put that in a formula form, it says that the rate of coal production is the initial amount times 10 to the t minus t naught over 20. If you don't believe this, plug in some numbers in your spare time and see if we're right. So that's called exponential because we have t to some 10 to some exponent. Here's another logarithmic plot, consequence of the Industrial Revolution. So we're going from, I don't know what this, this axis isn't labeled, but the graph is. So this is world population in millions. Here's 100. So this must be, this is 100, this next one is 200, this next one's 300. This is somewhere between 2 and 300 starts here, and then it goes on. England and Wales. What happened here? Did this go to 0? The funny thing about log plots, there is no 0. From 10 to 1, if I went down further, I'd go from 1 to 0.1, from 0.1 to 0.001, 0.01, 0.001, and 0.0001, etc. There is no 0. So this just got too low to plot on this graph. Notice UK pig iron, so this is iron generated starting 17, oh look, the Industrial Revolution, what do you know? and then start producing iron like crazy. And when you make iron, you can make ships, those kilotons of ships, plotted on a log scale. Let's do another example, for those of you who don't use log scales much. Every day, you start off with a penny, and every day you're going to double the number of pennies. I want you to write me into your will, because very shortly you'll be filthy rich. Day 1, day 0, you have 1 penny. On the next day, you're going to have 2. The next day, you're going to have 4, and so forth. I can plot them as number of days. This is 1 penny, 2 pennies. Oh, yeah. 1 penny, 2 pennies, 4 pennies, 8 pennies. Hard to read on a linear scale. This is linear because these tick marks are all equally spaced. If we put that on a log scale, the regular linear plot, first 5 numbers or so are indistinguishable on this plot. I had to make the plot tall so I could see these numbers, so I can't see these. If I plot that on a log scale, whoa! Day 0 I have 1. Day 1 I have 2. Day 2 I have 4. Day 4 I have, whoops, I must have missed a day. Day 3 I have 8, 16, so that's going to look like a straight line. What's that point there? This is practice in reading these things. Remember that each decade, is what we call it, starts at 1 and goes up to 10 times whatever you started with. So here's a 10 to 100. So what do you think this point is? This line is 20, 30, 40, 50, 60. 60 is between 60 and 70. 64, right. Just practice in reading those. All right. Where does Ohio get its energy? Coal. Big time. 82% of our energy comes from coal. The red is nuclear, about 11%. This is data from last year. Natural gas, about 5%. Petroleum, 1%. Notice that this is for generating electricity. When I say energy, I'm being careless because I'm using petroleum to drive my car. This is just about electricity generation. Petroleum is only 1%, so we're only 1% of our electricity is coming from burning gasoline. Hydro and other renewables, 1%. Coal. Where does our energy come from? Coal. Here are 100, whatever year I got this data, this is 2005, we had 119 coal-fired electricity generating stations. And they had a total of 23,000 and change megawatts of capacity. 64% of the state's total electric generating capacity in 2005. That's funny. In this thing, it says 82%. So if you believe these data, 65 up to 82, we're increasing how much we depend on coal instead of the opposite. These data come from different sources, though, so I'm suspicious. Ohio is the biggest coal energy producing state in the U.S. We are not the biggest coal producing state because our coal is dirty. We import it from West Virginia and places like that, but we burn it the most of anybody. And these are where all these plants are. If you go down to Muskingum County, there's on Route 60, you can see a very nice coal burning plant, and we have pictures of one coming up. It's kind of cool, you can see it if you're interested in coal.
I have a question with that. Is
Yeah.
that by percentage or is that by like actual amount of coal that we burn? Do you know what I mean?
It's actual amount.
Really?
Well, from the way it's worded, making Ohio the biggest energy producing state. Now I could go back to the source and read the text around the picture, but that's what I think. I'm not 100% positive. We're also a pretty industrialized state, so we use a lot of stuff. Here's a plot we saw the other day. Oil, well, first of all, let's look at the plot. So 1 million tons of coal produced in Ohio. So we were doing great because we had lots of coal. But our coal has a lot of sulfur in it, so it burns dirty. So when they passed the Clean Air Act, we started digging up less coal and importing more from West Virginia and Pennsylvania, places that have cleaner coal. So if you see the trains coming north, on the train tracks are full of buckets of coal, that's where they're coming from. So we can burn them. Coal combustion results in carbon dioxide. So here's a quote from this source here. Coal combustion emits almost twice as much carbon dioxide per unit of energy as does the combustion of natural gas. So to get the same amount of energy, coal is dirtier to burn than natural gas. Carbon from crude oil combustion is better than coal, but it's not as good as natural gas. So that's in the middle. So basically coal's the worst thing. But they all still emit carbon dioxide. So if coal is so bad for making carbon dioxide, why are we using it?
Cheap.
Cheap, abundant, and it's going to turn out, it holds a lot of energy, so we can get a lot of energy out of it. We have lots of fuel. We have lots of coal. Here's a picture of a coal truck coming up from West Virginia. So we have a strong motivation to use coal because it's cheap, a lot of energy per unit weight, and it's close to us, right? If we lived in Hawaii, it wouldn't be so convenient to bring it by train from West Virginia. But causes acid rain, emits carbon dioxide, which contributes to global warming if you want to accept that, and causes other kinds of pollution like particulates and stuff that make people sick. Sure is cheap. Typical coal plant is 38% efficient. 38%. That is converting the chemical energy to electrical. So you have a bundle of coal, there's energy in those chemical bonds, it's a hydrocarbon, you burn it, you create heat, the heat creates steam, the steam drives a turbine, the turbine turns a generator, the generator produces electrical energy. To get from the energy content of the coal to the electrical energy going down the wire, 38% efficient. It turns out that in energy producing terms, 38 is not a bad efficiency at all. People say, oh, well, I think something should be 90% efficient. Forget it, it's not going to happen. Anything, most of them are going to be way below 50, in fact, efficient. So we waste a lot of energy producing energy. So we have chemical energy that goes to thermal energy by burning it. The thermal energy generates the steam drives a turbine, that's the mechanical energy. The turbine rotates some coils of wire inside a magnet. I have slides. And that creates electrical energy, and so there's conversion losses at every step. Ooh.
The huge building is behind one of Ontario Power Generation's fossil fuel generating stations. This one uses coal. Other fossil fuel generating stations use oil and natural gas to make electricity. In essence, it's a factory that converts the energy from burning coal into a flow of electrons, or what is commonly called electricity. The electricity that powers the province.
Coal is shipped to the station by freighter or train, where it's then transferred to the coal yard. There, large machines called tractor scrapers arrange the coal into storage piles. A series of conveyors transports the coal into the plant, where it passes through enormous pulverizers that grind the coal into a fine powder prior to burning. The pulverized coal is fed into a large industrial furnace that is surrounded by boiler tubes filled with water. The intense heat from the burning coal heats the water in the boiler tubes and turns it into steam.
The steam is transferred under pressure at high speed through large pipes to turbines like these. It's this pressure and flow that pushes the blades of the turbine, causing it to spin.
The turbine is connected to a generator that contains a rotor. Large electromagnets are attached to the rotor that is located within coils of copper wire called the stator. As the generator rotor spins, a flow of electrons is created in the stator. This produces electricity that can be stepped up in voltage through the station transformers and sent from the station across transmission lines.
The steam from the turbine is condensed back to water using cooling water from the lake and pumped back to the boiler where it is reheated to continue the process.
All right. I'm going to go back to about here. And let's watch this description of the process again. Can I make this full screen? Would one of these things do it?
Oh, great. Right.
This guy? Okay, I can still press go. All right.
The flow of electrons, or what is commonly called electricity, the electricity that powers the province.
Coal is shipped to the station by freighter or train.
All right. Coal is shipped to the station by freighter or train. What powers those? Something. Gasoline, fuel. There's energy put into the system to ship the fuel to the plant.
Where it's then transferred to the coal yard.
Oh, how's it transferred to the coal yard?
There, large machine.
Oh, transferred to the coal yard by conveyor belts or something. Then there's these large machines.
Machines called tractor scrapers arrange the coal into storage piles.
What runs the tractors and scrapers?
A series of
More
conveyors
fuel.
transports the coal into the plant where
The conveyors, they use energy.
it passes through enormous pulverizers that
The pulverizer uses energy.
grind the coal into a fine powder prior to burning. The pulverized coal is fed into a large industrial furnace.
There's energy to transfer from one place to the other, and there's friction in those pipes that has to be
That is
overcome.
surrounded by boiler tubes filled with water. The intent
You got to transfer the heat energy from the boiler to the tubes of water, so there's a loss there.
heat from the burning coal heats the water in the boiler tubes and turns it into steam.
The steam is transferred under pressure at high speed through large pipes to turbines like these.
When the steam goes through those pipes at high speed, there's friction on the sides of the tube, so there's losses there.
It's this pressure and flow that pushes the blades of the turbine, causing it to spin.
The turbine blades have friction. There's more losses there.
The turbine is connected to a generator that contains a rotor. Large electromagnets are attached to the rotor that is located within coils of copper wire called the stator. As the generator rotor spins, a flow of electrons is created in the stator.
Okay, so we have two things going on. One is the rotor has friction because it's rotating, and there's a conversion of energy from the mechanical form of the rotation to the electrical form, and there's a conversion loss there. Just trying to give you some perspective of what we're talking
This
about.
produces electricity that can be stepped up in voltage through the station transformers and sent from the station across transmission lines.
Okay, so there's losses in the transformer, and then there's resistive losses and capacitive losses in the transmission line. So when people, I don't know what to do with that. Stop, I'm done. How do I get out?
Over to the right.
Oh, that worked. So when we say 38% efficient, that is the losses in the chemical to the thermal to the mechanical to the electrical. It doesn't include the fuel to get the coal to the plant, the fuel to grind it up and pulverize it and all that stuff. And also it doesn't include the energy we use to dig it out of the ground before it went on the freighter to come here in the first place. So 38% efficient that's optimistic, realistically. Okay, we were discussing coal and CO2. So typical coal plant's 38% efficient. Coal is the cheapest fossil fuel there is right now. Burning it generates carbon dioxide, but it also generates lots of energy for me to eat my Pop-Tarts. So it would be nice if we had a clean way to use it. If we could find out, so there's two issues with coal. One is we're going to run out someday, and the other one is the carbon dioxide. If we could figure out a way to use the coal cleanly, then maybe there'd be some hope, at least to keep us going until we can find more efficient other ways of creating energy. So people talk about carbon capture and sequestration. So the idea is you're burning coal, you're creating carbon dioxide, if only instead of releasing it into the atmosphere, you could crunch it up and hide it somewhere. All right? So that's what we're going to do. So there's two parts to this. One is the capture. How do you suck the carbon dioxide out of the process? And then how do you hide it? Carbon capture is done at the power plant. In the process somewhere of converting the coal to energy. And there's three different ways. One is before you burn the coal, one is after you burn the coal, and one is the fancy way of burning the coal. The pre-combustion, you gasify the coal. So the idea here is you have high pressure steam and hot air, you make them react with the coal without combustion. So there's a chemical reaction there, and it produces something called syngas, which is short for synthetic gas. Mixture of carbon monoxide, don't breathe it, and hydrogen. Hydrogen is full of energy. Boom! Right? So you produce the syngas, you react the water to produce CO2. The syngas are steam and water into steam. React with the water to produce carbon dioxide. That's known as shift conversion. Who cares? Then you separate the CO2 from the hydrogen. Hydrogen is pretty light. And then you burn the hydrogen. So this one, you gasify the coal and then you burn the hydrogen result. And the carbon dioxide comes out here and you compress it into a liquid and you hide it somewhere. Pre-combustion pros and cons. It's been done in oil refineries, so the technology exists. It captures about 90 to 95% of the carbon dioxide. That's good. It can be applied to natural gas and coal power plants, at least in principle. It's the lowest technology risk because it's been established already, at least for oil. And the nice thing about the hydrogen is you could burn it there and create electricity, or you could transport it somewhere where you need the energy. Right now, when you go over and flick on this light switch, all right, flick it on. When you flick on the light switch, somebody in Muskingum County is shoveling coal a little bit faster into the power plant right now. All right, I'm exaggerating. But when we turn stuff on, they have to ramp up those generators somewhere to produce the current because we need it now. We have to generate it now. That's a problem for solar energy, for example, where I need electricity at night and the sun doesn't shine at night. If I could have the hydrogen produced here, shipped to my house, then whenever I turn on the light switch, I could burn a little bit more hydrogen. The cons are, it's not ready to be scaled up for power production. So it's been demonstrated in oil refineries and demonstrations in small coal production, but not on a power production scale. And you need to build a chemical plant in front of the whole turbine. So that's some infrastructure investment. It has high nitrous oxide emissions, that's what NOx stands for, and that means you have to put scrubbers. And the scrubbers are expensive and they have their own set of problems. And then you're driving the H2 turbines. You're driving the turbines with hydrogen instead of carbon dioxide, not as efficient. Another way would be post-combustion. So in this one, you burn the coal first, because the other one, we gasified the coal and before we burned it. Here, we burn the coal, and then you take the exhaust gas and you put them through a solvent containing amines to adsorb it. You change the pressure or the temperature to release the CO2, and then you hide it. Okay? Pros and cons. The nice thing about this one is you can retrofit current plants instead of having to build a whole new plant so that you have the chemical plant in front of the turbine. The technology exists, and actually the technology is already used in the soft drink industry of all things. But it's expensive. You have to keep replacing the solvents, and it hasn't been demonstrated on a sufficiently large scale. So this one isn't ready for prime time either. Here's another post-combustion approach called chemical looping combustion, and this is a lot of awful chemistry. But basically the idea is you have a catalyst, you have multiple reactions, so you oxidize some kind of metal, you reduce the oxide with the burning hydrocarbons, and here's an example using nickel for you chemistry buffs. I'm an electrical engineer, so I'm not a chemistry buff, so I just kind of skip over that. But the nice thing is you're using nickel here, you get the nickel back. That's the catalyst. So as you loop through this process, you react with the nickel, you produce carbon dioxide. So here's the metal oxide, here's the metal oxide with extra oxygen, here's the fuel. So the fuel comes in and reacts with this, you get extra oxygen, produce CO2, come back here, and you reduce that back to the, or is it oxidized? That oxidizes, this reduces, I think. You add oxygen from the air, we have plenty of air here, and produce the metal oxide again. So you can reuse the catalyst. This technology is actually being worked on as a research project at OSU over on West Campus. I don't remember the building. But last time I talked to those guys, it wasn't efficient enough for prime time. But you'll see that in the literature, so you may want to know about it. And then, so we had the pre-combustion with the synthetic gas. We had the post-combustion where you treat the exhaust afterwards through chemical looping or the other way. And now the third way is oxy-fuel combustion capture. So the idea here is you burn the fuel in pure oxygen instead of air. So here's the fuel and here's oxygen coming in. So you get more complete combustion, and the resulting emissions are carbon dioxide, boo, and water, yay! Separated by condensation. That doesn't sound too bad. And then you hide the carbon dioxide. So the pros and cons of this, you could potential for capturing 100% of the CO2. Excellent. More complete combustion means there's fewer other pollutants like particulates and stuff like that. we may be able to retrofit existing plants. But the catch is, in order to burn the coal in pure oxygen, you got to generate the oxygen. That takes energy. So you can separate oxygen from air using cryogenics. With cryogenics, you cool things way down. If you ever walk by the parking garage over here, you'll see there's a giant nitrogen tank. It's about this big in diameter, and it's about from the wall to where I'm standing, filled with liquid nitrogen. We use that in the clean rooms in the basement for the research labs for cryogenics, to keep things cold. That tank of liquid nitrogen, they refill it 3 times a week. And a truck comes, so somebody somewhere is generating the nitrogen, and they compress it, and they make this fluid, and they put it on a truck with a lot of energy involved. Who cares? The interesting thing is that the tank has had problems with leaking a lot. So the company that makes the tank, they shut it down recently because they said their worst nightmare is there'd be a nitrogen leak on game day, and all the people tailgating in the parking garage would not realize that they're breathing pure nitrogen that's leaking out of the tank, and they would all fall down dead. That's bad luck, especially on game day. So they took the tank out, they're taking the tank out, and we're going to put another one in that's safer. So little juicy gossip for you. You need to produce the oxygen, and there's a high energy cost to do that, so about 15% of the plant's production. So if you combine this with chemical looping, maybe, because that way you can produce the oxygen too, might have potential. Not ready for prime time. And then coal produces more than just carbon dioxide. So we also have sulfur dioxide, which causes acid rain. Well, you can reduce that with scrubbers. They basically spray the flue gas after you burn with some limestone and water, and there's a chemical reaction. But that's expensive. Then there's nitrous oxides that contributes to the ozone layer, so that's going to have an effect on climate. Low nitrous oxide, low NOx, reduces nitrous oxide by controlling combustion conditions. There's some costs associated with that. And then there's particulates, so if you have asthma, you don't like those. You can put electrostatic those things in there and use static electricity. Oh, now I got to generate static electricity. Nothing's ever free. But coal sure has a lot of energy. And then there's the sequestration part. Where do you hide it? Well, one idea is to inject it into the ground. Nobody will ever find it there, so they compress it, and then they pump it down into the ground in these, this is a depleted hydrocarbon reservoir. I think that means they already fracked it or something. I don't know what that means. Here's a reservoir, trap and seal. Natural gas reservoir is here. I don't know what that means. And another one is offshore natural gas production with CO2 separation, sequestration. So they talk about putting it into the ocean or dissolving it in brine and pumping it under the ground. There's different ways to do it. This one, they want to pump it into a coal seam. So maybe somebody mined the coal. There's a coal mine down there that's abandoned. We could pump the carbon dioxide on here. How do you make sure the carbon dioxide doesn't get out? I don't know. I hope they have a way. I worry about this. Another one you can do is just pump it deep into the ocean, and it dissolves because of high pressure. So it'll stay down there, but the question is it changing the pH of the ocean and having an effect on the fishes and the other creatures that live down there? We don't know too much about this. What form is the carbon? Carbon can be pumped as a gas. It can be pressurized as a liquid. So if you took chemistry, you recognize a phase diagram here. We're plotting temperature versus pressure. And this is in atmosphere. So at 1 atmosphere, carbon dioxide becomes a gas at minus 78.5 degrees Celsius. But if you increase the pressure, it'll solidify. This is a low temperature. Here is room temperature-ish. So if you put enough pressure, you can create a liquid. In this range, basically, you can create the gas and make a liquid, or if you put a lot of pressure and cool it down, you can make it into carbon dioxide ice. So that's why you want to put it deep, because you need a lot of pressure. Pressurize it, cooled into solid, attached to other elements chemically. You could do that and make some carbonate material such as limestone and put that back in, but you've got to have the other elements to create that. So carbon capture and sequestration, some people just say CCS, has been demonstrated on a commercial scale, but it's not used in any coal power plant in the United States. I believe it was demonstrated on a commercial scale in an oil refinery, not a carbon plant. it would cost almost as much, about 90%, to retrofit existing coal plants with CCS as it costs to build the plant in the first place. But you recall from our last lecture that the number of coal plants was decreasing because a lot of them are getting near the end of life. So we're getting to a point, it was an opportunity because we could either build more coal plants or we could try to use this opportunity to use more wind and solar and stuff. Another opportunity to say, well, since I got to build a new coal plant anyways, because I don't think wind and solar are ready, just some people's opinion, maybe I'll build a coal plant that's got the chemical plant in front of it and I can have CCS built into there. So as long as I got to build a new plant anyways. And then there's concerns about whether the carbon actually stays in the ground or changes the pH of the ocean. There's a lot of unknowns. Is clean coal a solution for Ohio? Might be. I don't know. Maybe alternative energies are going to be so expensive for a while yet that maybe it's worth going to all this trouble. Costs almost as much to retrofit a plant, we just said that. But we're still going to run out of coal someday. So some say more than 100 years, some people say sooner. And we're going to, later in the semester, we'll look at how people make these estimates and learn to evaluate those because they use all kinds of different methods. But if we're going to run out of coal, then maybe, and CCS isn't really deployable yet, then the question is it going to be deployable within the next 100 years, or should we just skip this and go straight to renewables and put our energy, our efforts there? If coal is produced, if coal produces so much carbon dioxide, why do we use so much of it? This is where you all yell, it's cheap. Yeah, it's cheap. We have lots of it. Because we have lots of it, it's cheap. So take-home points. We need energy to prosper. We need energy to make stuff. We need energy to move stuff from place to place, including ourselves. We need energy to keep warm and cool. The more prosperous we are, the more people we can support. The more people we have, the more energy we need. The more energy we make, the more carbon dioxide we emit. Most of our energy comes from burning coal in Ohio. So we have more people, we need more energy, we create more energy, we burn more CO2. CO2 contributes to climate change. Just saying. I think this is an excellent point to quit because I see we're coming up on the end of class. And we'll start here next time. Let me just see what's coming up. Ooh, woo, woo. Okay, fine. I don't want to spoil the surprise. Are there any questions? Wow. All right. Run and play, and I'll see you next time.
Any reading?
Oh, yeah, read the next chapter. Yeah, it would be good to read the next chapter.